Hello again and welcome. Today we're going to be looking at some of the newer spark gap transmitters that I put together. This particular one can operate up to about 30 megahertz. You can see I'm basically just using hot glue and plastic here to make up the coil forms. Down here is the spark gap. There's a small disc capacitor across it and a small magnet and a bunch of ferrite loaded up on the one side of the coil. In the center we have our capacitor. It's making up the tank circuit. This is a small output matching transformer. Of course, this is the output of the transformer, and this is our tuning capacitor here. So this is the last one that I built. Again, we have the tuning capacitor. Here's our tank circuit in the center. Here's the output coil. Down here is our spark gap. Again, this is the high voltage input. This one has a couple of measurement meters. The meter on the left is measuring the aerial current, and the meter on the right is measuring the reflected power. You can see I'm now using wood for the coil forms. This is oak. It came from a tree in our yard. I cut that up and let it dry for about 6 months, and then sectioned it up on the table saw and drilled holes in it. There's just a bit of Teflon that's inserted between each hole. That's there just to prevent any kind of breakdown. Here we have the power supply out of the fly swatter. Again, this was meant to run off of 2 AAA batteries. I had tried to increase the voltage and I damaged the transistor. I since changed out the transistor for a lot beefier part, and you can see I've gone ahead and added this heatsink to this to overdrive it. And you may remember I had removed the output capacitor. This is a DC output. It was made to put out 2 kilovolts DC. And in our case, we're trying to actually modulate the spark gap down inside of the transmitter. Now, I have added this additional spark gap to the output of this. It's really there just to limit the output voltage and hopefully protect our transformer and output stage. Let's go ahead and we'll attach this to our transmitter. I saw Hackaday had published a story on these spark gap transmitters. It was interesting reading some of the feedback. One of the more common comments was people were all concerned about the radiated emission off of these transmitters. Again, I'm only dealing with a 200 picofarad capacitor, and if we calculate the amount of energy that we're storing, it's 1/2 CV squared. I'm limiting those first tests to 500 volts, and then of course watts is joules per second. So if we multiply that by the modulation rate, I was actually operating some of those early transmitters below 1 milliwatt. So we're not talking about a lot of power here. I had actually taken one of the first transmitters, I hooked it up to a dipole antenna that's up on the house, and I tried to go outside them with a radio and see how far I could actually transmit with that setup. And I made it to about in front of the neighbor's house, and I couldn't pick it up anymore. So we're not talking about a lot of radiated power. This is where we would attach our antenna. Of course, the back one here is for the ground. Let's go ahead and we'll attach our oscilloscope to the antenna lead. I'm just going to run this from our bench power supply right now. So you can see our scope is triggering. Let's go ahead and we'll zoom in a little bit. So here's the output of the transmitter. And again, with this tuning capacitor, we can change the output frequency. This transmitter will operate down to about 6 megahertz and up to about 11 megahertz. In those first videos, I was using a ham radio that's made by Drake. It's an old vacuum tube type radio. It takes a long time to warm up. I was looking for a portable radio that I could use over a wide frequency range. I was looking for something that would work down to maybe 500 kilohertz, up to maybe 200 megahertz or so. And I wanted to be able to demodulate AM, FM, sideband for that entire frequency range. I settled on this radio. This is made by Tecsun. It's a model PL-990. This radio doesn't do everything that I want, but for a general purpose radio, I do like it. It's actually fairly sensitive and low noise. It's got some hot spots that the receiver picks up its own internal oscillators, but for the most part, those haven't really been an issue when using this radio. Let's just go ahead and turn this thing on. You can see I've got this sitting right next to this spark gap transmitter, and I'm picking it up right now. Let's just put it over here. You can see we're what, maybe a half a foot away. Let me turn up the volume a little bit. And now let's go ahead and tune our transmitter. Right there's the peak. This is all the way with the plates apart, or the highest frequency at 10 megahertz. And here they are, fully meshed. Again, we'll look at the peak. Again, with this fly swatter, as I change the voltage, you can hear how it changes the frequency. But it's very detectable. Let's try changing the tuning now on our radio. This will be a little difficult to shoot with the camera. So what I'm going to do is retune our radio to find the peak. Right there we have it. I'm going to adjust the radio receiver and see where the signal falls out at. We'll turn up the volume a little bit. And you can hear the signal very solid there. So this is roughly 7.7 megahertz. It's peaking at about 7.48. And this is about 7.2 or so. So let's try skipping it up a bit. Here's 9.7. Here's 11.45. 13.5, 15.9, 17.4, 18.8, 21.4. Let's go to the AM broadcast band. Let's try it on the FM broadcast band. Again, let's go back to the AM band. So if I tune this to a dead spot, let's try bringing the radio closer. Right here you can hear it. You can see I'm still about 1.5 feet away. You can hear them like maybe a foot. Let's just try attaching an antenna to it real quick. We'll just be using our finger. You can see I can just barely pick it up. Again, looking at the 2 meter movements, the one on the left being the aerial current. What I'm going to do is just short the antenna to the screw here at the top. This happens to be at ground. And you can see there's just a slight deflection. You can see the SWR goes down a little bit. This is really limited by the amount of power we're putting out. Let me just go ahead and turn up the power supply a little bit. Again, that little bug zapper cannot put out a whole lot of power. We're limited to well under 1 milliwatt with that. So to get even more power out of this, we'll have to drive it with a separate power supply. Again, we don't have to drive the transmitter with AC. We can do it with DC. Here we have our ESD gun. Again, this is capable of putting out about 5 kV. What I'm going to do is connect this directly to our transmitter. So we'll attach the ground here. And here I have a 2 mega ohm resistor. We're going to place that in series with our spark gap. Out here we'd have our DC high voltage supply. Here's our 2 mega ohm resistor. And then this is our transmitter. So again, we've got a spark gap, and that's in series with a capacitor, which is in series with our inductor. So this L and C make up our tank circuit. Again, this capacitor is currently set for 200 picofarads. Again, what's happening here is we turn on our high voltage power supply. This capacitor is shorted, so all the voltage is dropped across this resistor. It starts charging the capacitor through this inductor to ground. As this voltage gets up high enough, eventually this gas discharge tube fires, shorts this tank circuit to ground, and this will begin to resonate. That's coupled onto our secondary tank circuit, which again is just a large inductor, and we have a tuning capacitor to adjust the resonant frequency. and then we have our antenna attached onto that secondary as well. So the frequency that this is going to run at, I'm not talking about the RF frequency, but the cycle time, how fast the spark gap fires, is determined by the voltage of this supply, the breakdown voltage of our spark gap, and the RC network here. Now watch the meters as I slowly start turning up this voltage. See how the SWR is coming up? Okay, so this resistor is a 100 ohm. Let's go ahead and short that to ground. As a matter of fact, just watch the meter on the left as I start putting my fingers across that 100 ohm resistor. See how the aerial current starts to increase? Of course, if there's nothing attached to this, it's going to have a very low aerial current. It doesn't have anywhere to go. As I grab hold of this, my body is coupling onto the air around me, and the current starts to go up. Watch what happens now as I touch our resistor straight to ground. See how much higher the current goes up. Now again, the cycling of this is very slow right now. So again, the faster I'm able to cycle this, the more power we're going to deliver to the antenna. Here I have a clip lead. Let's just go ahead and attach that to the antenna directly. And again, you can see just connecting that, the SWR comes down a little bit and we start to get some current. Let me go ahead and touch my finger to the end of that wire. You can see it improves the match quite a bit. Let's try tuning it a little bit. You can see, oh, right there is our sweet spot. So the higher the frequency, the better the match. It's not quite perfect. We're still getting quite a bit of reflection. Again, because the output of this is a dampened waveform, we can use a standard AM receiver to listen to the frequency of this. So if we set this for 500 Hertz or something, we should get a nice pleasant tone like we did with our first demonstrations. So that's the whole reason I don't want to run this with DC, is it would be very difficult to set this frequency up. So driving this with a car coil that is able to run over a very wide frequency range, we should be able to get a decent tone out of this transmitter. So here's the receiver that I made. This started out as a glass fuse. I removed the two metal caps and the element, and then I machined up two brass inserts, and then the ends of these are cut on a slant, and then I filled this up with some metal. Now originally what I did is I went to the cutoff saw, I took a magnet and I just pulled out whatever happened to be in there, and then I took the magnet in a paper towel and then I pulled the particulates across the paper towel, basically looking for ferrous material, and then I sprinkled some of that inside of the glass tube. Failed miserably. I read online that people were using nickels, so I took a nickel and I filed that down. I sprinkled some of that inside of this. That didn't work either. I ended up with a mixture of these two metals, and for some reason that happens to work. So let me just turn this thing on, and you can see I have a small LED, and here I have a small piezo grill starter. Let me just go ahead and ignite this, and you can see the LED turned on. Now to clear this we have to shake it like so, and just fire it again. Now I'm probably maybe a foot or so away from this, and we're picking it up just fine. And of course I don't have any antennas attached to this. You see it's very reliable. Let's try it again from maybe 4 feet or so away. Oh, just barely triggered it. You can see it's starting to glow. It's not as intense as when we get closer. Again, this is about maybe 1.5 feet away. But again, we don't have any kind of an antenna on this thing right now. But this is basically how the early receivers worked. They had a mechanical means to reset the cohere. Some of the later coheres, I guess, were actually automatically resetting. But by that time we started to see other types of detectors that basically obsoleted all the coheres. But to me the real interesting thing about this is, let's go ahead and turn on our spark gap transmitter. So that transmitter is running right now. See, we can't pick that up. I mean, it's right next to the transmitter. Let's try bringing it close to the spark gap. See that? Even that close, it will not pick it up. So if you don't think that this is functioning right now, you can see the little sparks coming off it. Let me just go ahead and turn up the voltage a bit more. Let me go ahead again, we'll try this with our grill starter. You know, I'm real close to it, but I'll go ahead and fire this off one time. You can see it instantly kicks it. You can see it's just very easy to pick that up. But sitting right next to our transmitter, nothing's coming off it. So I'm not sure if it's because of the wideband noise coming off of this grill starter versus our spark gap transmitter that is essentially a tune circuit. Maybe this is sensitive to a certain frequency range. I don't know, I've never looked into it. I'm just amazed that they were able to get some of this stuff to work as well as they were. Just for example, if you read up on coheres, just the doping or the mixture of the metals that they were using, it was quite critical to get the sensitivity out of these. Think of all the testing that somebody had to do to sort that out. I mean, here in my lab, you know, I've got this oscilloscope sitting here. You could imagine the pioneers wouldn't even have a conception of what this piece of equipment was back then. Looking at some of the power supplies that I've used for experimenting with these spark gap transmitters, this is the one out of the fly swatter. You can see where I damaged the transistor and I replaced it with a much larger part. Now the output side of this goes through a doubler. It was originally DC, it still kind of is, but there was a output capacitor that went in place of the spark gap, and obviously I'd removed that for my testing. This works fine for a lot of the experiments that I've ran. I wanted to make something with a little bit more power, and so I've got these transformers here from Amazon. Wasn't very expensive, and I've got a MOSFET here that I'm using to drive it. The way I use this, I just attach this to the function generator, and then I can set the frequency as well as the pulse width to control the drive to the coil. And then I attach this to a heatsink depending on how hard I drove it. The problem with using this type of coil is this won't operate over a very wide frequency. Also, like the fly swatter, it doesn't deliver a lot of power, so I'm pretty limited as far as what I can get out of the transmitter. This power supply came out of an air cleaning system. It's been slightly modified. This will provide quite a bit more power than the fly swatter. The problem is, again, the output of this is DC, so again you're limited as far as trying to modulate the spark gap. So really what I'm looking at again is using the ignition coil out of a car. Think about your car maybe idling at 500 RPMs or so. Maybe for a high performance car you can take it up to 20,000 RPM, and it'll certainly provide more than enough power for the experiments that I run. So off to the left you can see I have a little driver circuit. This is nothing more than two 555s. The left one is set up as our oscillator, and then the one on the right is our one shot. So I thought I'd show you one of the problems when experimenting with this kind of stuff. So attached to the coil I have a small alligator clip. This is making up our spark gap. So let me go ahead and I'll power this thing up, and you can see the one pot here sets the pulse width or the dwell time of the coil. I'll zoom in this a little bit further. Typically for an automotive system you're looking at a millisecond charge time. You can see the oscilloscope is currently set for 500 microseconds per division. So we are somewhere under a millisecond charge time. The reason that I've set this so low is I really don't need the kind of energy that this coil can produce. Now our other pot here is setting the output frequency. You can see I can adjust this up to about 500 Hertz and as low as about 120 Hertz. And the reason I chose these frequencies is if you're going to run a spark gap off of the AC line, here we use 60 Hertz or double that, so say 120 Hertz. It was quite common for some of the rotary spark gaps to run at 500 Hertz. So that's setting my upper boundary. So let me just show you what happens if I power up that coil. See what this is doing to my oscilloscope? Of course, off to the right you can see I have a USB mouse attached to the oscilloscope. USB is not a very good bus to use in a high noise environment like this. What will happen is the mouse will typically reset A lot of times it just flat out won't come back and you have to power cycle it. Basically unplug the cable, plug it back in to reset it. You can see this is located maybe a foot away. There are no antennas or anything attached to this coil. So this by itself puts out more than enough noise to knock out the scope. Of course, part of the problem with this is we're building this on a breadboard. This is all susceptible to the noise that this is putting off. That's why you see this thing double bump the way it does. Eventually the idea is that all this is going to be built up on a board. So I've gone ahead and transferred my breadboard over to a section of circuit board material. This is what it looks like. Again, this is nothing more than a couple of 555 timers. And the one on the right is set up for the oscillator. And again, this is the one shot that programs the dwell time for the coil. You can see I've added a small TVS. There's a diode in series for reverse polarity protection. And there's also a MOV for any kind of large transients. You can see the two potentiometers. The one sets the dwell, the other one sets the frequency. This can be programmed again between about 130 Hertz and 690, and the dwell time can be between about 375 microseconds and 500. This is a BUP 314. It's an obsoleted IGBT. One of the things with this, I can just drive the coil directly, but you notice that I don't have a heatsink on here at all. This thing's going to run ice cold driving this coil the way that we're going to run it. You can also see, instead of using all the through-hole parts, a lot of these now are changed over to surface mount. The basic advantage to using those is I can pack a lot more in a small area. Or in that, there really is no benefit for this particular circuit. But yeah, this is really a mess. I didn't spend a lot of time with it, but it does work. So what we're going to do is take our same ignition coil and we're going to attach that to this driver. We're also going to bring out our telegraph key and we'll just attach this in series with the power to our test board here. We'll attach our oscilloscope. This test point is used to look at the gate drive of the IGBT. We'll just clamp the clip blade here to ground like so, and we can just run this off of our bench power supply. Alright, so let's go ahead and we'll turn it on. You can see the LED here turns on, and you'll also notice that we get a waveform up on the oscilloscope. Again, this potentiometer on the right is setting the frequency. Currently this is reading 688.7. That's in Hertz. And let's just zoom in here a little bit. And again, this one is setting the dwell time. This is 500 microseconds per division right now. And you can see I can speed that up. This is about 375. Again, that basically sets how long we're going to be applying voltage to the coil to charge this up. Let's go ahead and we'll attach the ignition coil. Okay, and I'm going to put this right next to the oscilloscope. Alright, let's go ahead and turn on our power supply. And I want you to notice that the scope is no longer glitching. Let's increase the gap. See how stable our oscilloscope is now? Let's go ahead and change the frequency. Try opening our gap up a little bit further. Have to increase the dwell time a little bit. Let's try moving it closer to the center of the scope. So this is one of the problems that you can run into when you're building high voltage circuits up on a breadboard. You have a lot of parasitics that you have to deal with, and of course those can cause other problems like affecting your oscilloscope. You can see now this is very stable. So I'm currently running the power supply off the PC. You can see I'm toggling it on and off at a 1 Hertz rate. We just go ahead and we'll attach our antenna output to the chassis ground. And you can see our aerial current is going up quite a bit. This knob on the left, this controls the sensitivity of that. This is just a clip lead, and I'm going to say it's about 6 feet long, and it's going up to the fan in the office. And you can see we're measuring a little bit of aerial current. The VSWR is still quite high. This is what the transmitter sounds like. What I'm going to do is take this radio outside and let's get an idea how far we're transmitting. You can see I have our receiver set to DX. The antenna is extended. It's not very far up, but that basically is where our office is. The office again is up there on the left. Signal is still quite strong. Let's try the AM broadcast band. It does not appear to be interfering with that. Let's try the FM.
Has not showed up on the late evening.
Again, no interference from that. Alright, I'm sitting in my car. Got the dog with me. We're going to go for a little drive. Let's see if we can get maybe a block away or so. I'm currently about a block away. And you can see we cannot pick it up. So less than a block. Alright, we're back in the house. Go ahead and turn the radio back on. You can see the transmitter is still working. Go ahead and disconnect the antenna. So I've read a few books and papers that were published around the time when they were first developing radio. And it was interesting because they were talking about, for ham radio operators, they were basically allowed unlimited power. So whatever they could muster up, that's what they had. 10 miles for them was a big deal back then. Again, if we're looking at this particular transmitter, I'm using a 200 picofarad capacitor, and my gas discharge tube is 1600 volts. So joules, or the energy, is equal to 1/2 CV squared. It gives us 2.56 e to the minus 4 joules. It's not a whole lot. Now watts is equal to joules per second, and we're driving this thing, we said, at 680 hertz. That's with it cranked all the way up. So if we multiply 680 hertz by our energy, that gives us 174 milliwatts of power. Now again, we're driving that into a clip lead antenna, which is maybe 5-6 feet tall. It's certainly not tuned for this frequency, so you could see the VSWR was still quite high, and we weren't registering a lot of aerial current. So with this poor configuration, I couldn't even transmit a block. Now, I would imagine if we hooked this up to a tuned antenna, we could probably transmit quite a bit further. I don't know how far. Again, it was never really a goal to see how far we could transmit with a system like this. Of course, we're able to radiate a lot better with this configuration than what I was with the original two transmitters, using our little fly swatter as a power source. A couple of things I'd like to do with this transmitter yet is probably make up some kind of a box to hold our car ignition coil, maybe use a smaller coil. The other thing I'd like to do is make some kind of an automatic keyer for it. So maybe in the future I'll show you what that looks like. Hopefully you've enjoyed having a look back in the history of radio. Things were a lot easier to construct back then, but as far as transmitting long distances with a system like this, certainly not trivial. Well, all for now. We'll see you in the next video. Later.